Let's solve a problem of finding the area under a curve. First, we'll use an integral to get the exact value. Then we'll back up and we'll look at how the integral is defined in terms of a Riemann sum that can be used to approximate the area under the curve. It's really important that we understand how Riemann sums work and how they relate to the integral that will give you the exact solution. Because every application problem that we do in this class from this point forward is going to depend on us understanding how to set up an integral to solve that problem by understanding how a Riemann sum could be used to approximate the solution. Let's get started. We want to find the area between the curve y equals 3x minus x squared and the x-axis. In other words, the area under this curve. It's always a good idea to start by getting a rough sketch of what your function looks like. So let's do that. We have ourselves an x and y axis. Let's take our equation, y equals 3x minus x squared. And let's see if we can figure out a rough idea of what this graph looks like. We don't need to get a perfect graph. We don't need to plug in lots of different x values and work out exactly what the y value is and get the exact graph. We just need to know a rough idea of where it is in the plane, what sort of shape it is, is it positive or negative, what are the boundaries of the region we're trying to find the area of. So a good first step is to figure out where this graph crosses the x-axis. We can do that by setting y equal to 0. 0 equals 3x minus x squared. This is a polynomial, so we know that we can solve an equation like this by factoring. If we factor this, we get 0 equals x times 3 minus x. And of course, if a product of two things equals 0, then we know that one of those two things must be 0. So we can say that either x equals 0 or 3 minus x equals 0, which would mean that x equals 3. So now we know the two places where the graph crosses the x-axis, because when y equals 0, x can equal 0 or 3. Let's label these on our axes here. Let's put maybe a 1 here, 2 here, 3 here. And our graph crosses the x-axis at 3 and also at 0. What does the graph do in between these? Well, we know that it's a parabola because we have 3x minus x squared. That's a quadratic equation, therefore we have a parabola. In fact, it's a parabola opening downward because the coefficient on x squared is negative. So the only possible graph that this could be is a sort of a hump or a curve that goes up in between these two x-intercepts and then goes down on the other side of it. So it looks something like this. And that's our curve. Now, what is the area that we're interested in? Well, the area that we need is the area between the curve and the x-axis. That's this area right in here. Now we're ready to set up and solve the integral that will tell us the area under this curve. For an integral, we always need an integral sign. We need to know our lower bound and our upper bound on the x value. We need to know our integrand, and we'll need our dx. What values does our x range in between? Well, if we look at all of the x values that border this curve, our x starts at 0 and goes all the way up to 3. So we know that our lower bound is 0 and our upper bound is 3. We need to find our integrand, but that's easy. It's just the function that we're actually finding the area of. It's going to be 3x minus x squared, and then we have our dx. Don't worry about these parentheses too much. They're just there because technically dx is being multiplied by the whole integrand. But we don't really need to worry about dx in this particular integral because the integral is very easy to solve. So the parentheses are there, don't panic about them. Let's solve our integral. This integral equals, well, this is an easy one. We just need to find the antiderivative of each of the terms that are being added or subtracted in our integrand. So the antiderivative of 3x is going to be 3x squared over 2 minus the antiderivative of x squared, which is x cubed over 3. And this is evaluated at 0 and 3. Our final step is to plug in our bounds and subtract the results. So let's use some brackets here. Let's say we've got 3 times 3 squared over 2 minus 3 cubed over 3. These brackets aren't really doing anything except visually setting off this part of the integral. And minus the quantity 3 times 0 squared over 2 minus 0 cubed over 3. Lucky for us, the second portion of our result is just 0. This part here. And the first part, you can work it out for yourself for the most part. It's going to be 27 over 2 minus 9 minus 0. And the result is going to be 4.5 or 9/2. And that is the exact area under the curve of this function. Not a bad idea to check whether our answer is reasonable. There's a few things we should think about. One thing is, we're looking for an area. This is not a signed area that might be negative or anything like that. It should be a positive number. And it certainly shouldn't be 0 or anything like that. So the fact that we've gotten a positive number is reasonable. Looking at our graph, can we get a sense of whether the area ought to be, around 5, around 10, around 100, around 0.5? We can estimate. We can look at this. We can actually, at this point, plug some numbers into our functions. For example, if we plug 1 into our function, we get y equals 3 minus 1, which is 2. So this is about 2. My graph is not perfect, so it's probably a very rough estimate. Well, if we plug 2 into our function, we'll get 6 minus 4, which is also 2. So it should be right about there, right? This actual maximum point is a little bit higher. In fact, you could use some skills from Calc 1 to find the exact maximum value, the local and absolute max of this function, but you don't really need Calculus 1 skills. We know that's going to occur when x is 1.5 because the parabola is symmetric across the vertex. You could plug 1.5 into your function, you would get 2.25. So that is the maximum height that we reach. So we could estimate the area under this curve pretty easily. We could say, well, it fits into a box that is clearly too big for it, that is 2.25 by 3. So the area definitely must be less than 3 times 2.25, which is 6.75. The area ought to be less than the area of this big box, and it certainly is. It's less than 6.75. In fact, it's probably maybe somewhere around half that size. 4.5 is probably a good estimate. So your BS detector that's checking whether your answer is reasonable should say, yes, I think this answer is reasonable. Now let's think about this problem in a different way. Let's forget everything that we learned about integrals and just think about how we could approach this problem using geometry. We're looking for the area under this curve. Well, in geometry, we know how to find the area of a rectangle. That's easy. Area is length times width. We could find the area of a triangle. Here's the base. Here's the height, and the area is 1/2 base times height. We even know how to find the area of a circle, but we don't have any tools to allow us to find the area under some other shape of curve. We can't do that. We can't get the exact area of this curve by geometry because we don't have a formula for it. But we can approximate the value. In fact, we've already tried that. We already tried approximating the area under this curve by saying, what's a rectangle that I can fit my entire curve into? And we did that already. We said, all right, here's a rectangle whose height is 2.25 and whose base is 3. And the area of that rectangle is 2.25 times 3, which is 6.75. And since our parabola is smaller than that rectangle, we know that the area of our parabola is less than 6.75. We can figure that out even without calculus. This is important because there are lots of problems in real life that we can't get an exact answer to, but we can approximate the answer. And that's really, really helpful. In this case, knowing that our area is less than 6.75 means it's less than 100. It means it's less than 1,000. The fact that our parabola is not much smaller than that rectangle means our area is probably more than 1. There's a lot we can do with this approximation, even if we don't know the exact value of the area. But how can we improve the approximation? Well, what we can do is use more rectangles. In fact, for Riemann sum, what we do traditionally is slice up our region into lots and lots of little rectangles and find their areas. Let's look at an example. This time, let's slice our region up into 3 rectangles. Okay. We're going to slice up our rectangles into 3 vertical rectangles, all lined up side by side, stacked up along the x-axis. So one of our rectangles is going to go from 0 to 1, and it's going to go up from there. Our next rectangle will go from 1 to 2. We'll go up from there. Our next one will go from 2 to 3. We'll go up from there. There are 2 questions we need to answer about these rectangles. What are the widths and what are the heights? Well, the width is easy. The width is just whatever the distance is along the x-axis for the base of your rectangle, whatever the change in x is when you go from 0 to 1. We'll call that delta x, and that is equal to 1. This width here is also delta x, which is also 1. This width here, again, delta x, which equals 1. So the width is easy. Call that delta x, which in this case is 1. We call it delta x because you're looking at how the x changes as you go from one rectangle to the next. Change in x is delta x. The next question is, what's the height of this rectangle? Well, maybe I'll just go up until I hit the curve itself. Now, if I just fill in this piece here, it's not a rectangle and it's a curve and I don't know what the area is, so I'll just make it a rectangle and know that I'm going to get an overestimate of the area, but that's okay. Here's my rectangle. So the first rectangle, the height in this case is 2, because the height of a rectangle is 2. Let's make the next rectangle. Well, maybe I'll start from here. Maybe I'll start on this side here where the x is 2, and I'll go up until I hit my curve, go over, which again happens to be at 2. It's just a coincidence they happen to be the same value here. Don't assume that that's always going to happen. So my second rectangle my height is 2 again. What about my third rectangle? Well, if I follow the pattern that I followed for the first 2, I want to take the right side of the base of that rectangle and go up until I hit the curve, except, whoops, I'm already at the curve when I'm on the x-axis. So in fact, my third rectangle doesn't have any height at all, it just goes here. In fact, I'll need to erase the bit that I already made of my rectangle. So my third rectangle actually has a height of 0. It's not really a rectangle, but mathematically it still counts. Okay, now I want to know what the area of my entire curve is. To work that out, I need to find the areas of my rectangles. So that's easy. The first rectangle, the area is going to be the height times the width, which is 2 times 1, which is 2. My second, again, height times the width is going to be 2 times 1, which is 2. And my third, the area is the height times the width, which is 0 times 1, which is 0. So our total area is 2 plus 2 plus 0, which is 4. Now again, this is just an approximation. This 4 is the area of the shaded parts in blue that I drew. It's not the same as the area of the parabola. Notice that it's a little bit less than our previous estimate of 6.75. But also, do we think that it's an overestimate or an underestimate of the area of our parabola? I would say it's an underestimate. Notice that one of our rectangles overhangs the parabola, but the next two go inside the parabola. They're smaller than it. But the bits of the parabola that stick out outside the second and third rectangles seem to be a bit bigger overall than the bit of rectangle that sticks outside the parabola. So it seems like overall there is more area missing from our estimate than there is excess. So our estimate is probably a bit of an underestimate. The parabola has an area a bit more than 4. And of course we already know this because we did find the exact area, which is 4.5. Now let's improve our approximation of the area under this curve. The best way to do that is to use more rectangles. In fact, let's use 6 rectangles instead. The number of rectangles, which we'll call n. In this case, we'll use 6. What's the width of each of those rectangles going to be now? Well, I need to take this portion of my x-axis that I care about from 0 to 3 and cut that into 6 equal pieces. Those cuts are going to happen here, 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 and then of course at the endpoints. So my delta x, which is telling me the width of each rectangle, well, I can find the width of my entire interval, 3 minus 0, and divide by the number of rectangles. That's going to be 3 divided by 6, which is 1/2, or 0.5. You can use a decimal or a fraction, whichever you prefer. Okay, so my actual x-coordinates of those cuts are going to be at 0.5, 1, 1.5, 2, 2.5, and 3. Now, we're going to have more rectangles. That means a lot more numbers to have to deal with. Let's keep ourselves organized. So let's go here. Let's look at let's make a chart. Let's make a list for each rectangle that we're on. From 1, 2, 3, 4, 5, and 6. I'd like to know what the height is of each rectangle, and we'll fill in some more as we get to it. So rectangle number 1, that's the rectangle where the x-coordinate goes from 0 to 0.5. And as before, let's take the right side of that subinterval here. Let's go up until we hit the curve. And we'll go over and make a nice rectangle out of that. How do I find the height of that rectangle? Well, I just need to know what happens if I plug 0.5 into the function that describes this curve. That's going to be f of 0.5. Plug the x value into the function to get the y value. In that case, that's going to be 1.25. For my next rectangle, we'll go from 0.5 to 1. We're choosing to use the right side of each subinterval to determine where your rectangle should hit the curve. So our right side is 1 here. We're going to go up till we hit the curve. We've already done this. We know if you plug 1 into the curve, you get 2. So the height of this rectangle is 2. And again, that is f of 1, which gives us 2. Plug the x-coordinate into the function to get the height of the rectangle. For the third rectangle, we're going to use the right-hand side of that interval on the x-axis, which is at 1.5, and we'll again go up until we hit the curve, go over and make our nice rectangle here, and we are going to plug 1.5 into the function, f of 1.5, which gives us 2.25. We've already done some of the work here, so that's saving us some time. Okay, just keep going. For our fourth rectangle, the x-coordinate we're using is 2. We'll go up until we hit the curve and go over. That height is 2. That's what we get if we plug 2 into the function. So f of 2 happens to be 2. For our fifth rectangle, we'll take 2.5, which is the x-coordinate, plug that into the function, and get our height of a rectangle. If you plug that into the function, you're going to get 1.25. So f of 2.5, plug it into the function, y equals 3x minus x squared, and we get 1.25. What about our sixth rectangle? Well, we're going to take our right-hand side and we're going to go up until we hit the curve, except, oops, we're already at the curve. So again, we have a rectangle whose height is actually 0. F of 3 is 0. So this is really important. The height of each rectangle is just the y value that corresponds to the corresponding x value for that rectangle. It's what you get by plugging the x value into the function. Okay, what's the width of each rectangle? Well, the width of each rectangle is always the same. It's going to be our delta x, which is 0.5. What's the area of each rectangle? We just need to multiply the height times the width. So 1.25 times 0.5 is 0.625, running out of room here. Okay, 2 times 0.5 is 1. 2.25 times 0.5 is 1.125. 2 times 0.5 is again 1. 1.25 times 0.5 is 0.625. And 0 times 0.5 is 0. We've found the areas of all 6 of our rectangles, and our last step is going to be to add them together. So let's think about the actual process that we're following here. We're taking a sum. The Greek letter sigma, capital sigma, represents the sum. There's some additional notation here. I don't want to worry too much about the details of that, but we're adding these things up. What are we adding up? We're adding up the areas of all our rectangles, and the areas are always f of x, f of whatever x coordinate that rectangle uses, times the width of each rectangle, which is delta x. This is our approximate area. Again, there's more notation here to make this more precise. I don't want to get into the precise notation here. I just want you to see the pattern. We're taking each height of each rectangle times the width of each rectangle. That's the y value of the function when you plug in the x, times the delta x, the change in x. And then this sigma means add those all up. We can add those up. We're going to have 0.625 plus 1 plus 1.125 plus 1 plus 0.625 plus 0. And we'll get 4.375. That is our approximate area. Notice that this is a somewhat better estimate than what we got using 3 rectangles. With 3 rectangles, remember one of them had 0 height, but there were still 3 of them. Using 3 rectangles, we got an area of 4. This time, with 6 rectangles, we got an area of 4.375. Since we already solved the problem exactly using integral, we know the real answer is 4.5. The interesting thing is that as we increase the number of rectangles, we get closer to the exact value. So using 6 rectangles, we get 4.375 here. Again, I don't want you to worry too much about the details, the minutiae of doing these computations. The important thing is that we understand how these computations relate to the symbolic nature of an integral, and how that will tell you how to set up an integral to solve a problem like this in the future. What if we tried to get an even better estimate using lots of rectangles? Let's say that n is the number of rectangles, and it's a lot of them. What would be our delta x, the width of each of those rectangles then? Our delta x is going to always be the width of our entire interval, which is 3, divided by n. If n is really big, then delta x is very small. And in fact, we can see that if I slice up my region to lots and lots and lots of very, very, very narrow pieces. So we can see this. If you use, let's say we're on this rectangle right here. Here's our delta x. It's very small. In fact, let's suppose we're looking at this particular rectangle right here. So we're going to go up till we hit the curve, go over, make a rectangle. That rectangle is still leaving out a little bit from that curve, but the amount that gets left out or overhung is going to be less and less and less the more rectangles we use. Let's look at the details of this rectangle. Each rectangle, well, the width is still going to be delta x, whatever that happens to be. The height is obtained by taking the x-coordinate associated with that rectangle. Here is the x-coordinate we care about, and plugging that into the function to figure out what the y is, or the f of x. What is the area of each rectangle? Well, it's going to be the height times the width. It's going to be f of x times delta x, whatever that is. We're going to have to work that out for each rectangle individually, and to find the area of the whole thing approximately, to find the approximate area under the whole curve, the approximate total area, well, we'll need to take that f of x times delta x once for each x value that we get for each rectangle. So this symbol here gets computed lots of different times for all the different x's. And then we need to take the sum of all those, add them up. Now, again, there's some more notation in here to make this formula precise, but I don't want you to get hung up on that notation right now. The important thing is to recognize what this formula means. It means we are taking the area of each rectangle, which is going to be the height of the rectangle, times its width, and we're going to add those up. That will give us our approximate total area. How do we improve this answer and get better and better and better answer? In fact, how do we get from this to the exact value? Simple. We let our n, our number of rectangles, get bigger and bigger and bigger. In fact, let's take the limit as n goes to infinity of sum of our f of x times delta x, and that is going to be the exact area. And we have a new notation for this. The notation for this is now the integral from our lower bound to our upper bound of the function. And letting our n go to infinity means letting our delta x get smaller and smaller and smaller down to this infinitesimal value that is essentially 0, but not exactly. We call it a differential, and now we call it dx. And this right here, notice that the integral notation is essentially saying the same thing as the summation notation for Riemann sum. This S for integral means a sum, essentially. You're going from your bounds from A to B. That means that x is ranging between A and B. And you're adding up these infinitely many, infinitesimally small things that you get as the areas of these very, very, very thin slivers of rectangles whose heights are f of x and whose widths are dx. And this is the connection between the Riemann sum that approximates an area using geometry and the integral that computes an area exactly by introducing this limit as n goes to infinity. Now in practice, we don't solve integrals by doing sums at all. The reason for this is because we have the fundamental theorem of calculus that tells us that, as amazing as it seems, an integral is the opposite of a derivative. An integral can be solved using an antiderivative. So the process that we follow to actually compute integrals most of the time is totally divorced from this idea of a summation. But we still have to understand the idea of a Riemann sum in order to help us set up an integral that we need in order to solve a problem that we care about.